Okay, so our equation for the Mars helicopter can be seen right here as an acceleration function. And we have multiple known factors as well. So you can see that little t is equal to negative t, which is the time from launch to rest. And then we have beta and alpha, which are both known constants in our acceleration function. So we can get those canceled out quite easily. And we also have d, which is a known constant, which is a distance that the helicopter traveled. And we researched the actual helicopter itself, and it traveled 100 meters across Mars to get to the rover. So we set d equal to 100 in our equation in meters, and we're trying to solve for big T. So that's why we have a question mark here. And then we have our velocity function, which is integrating our acceleration, and then our position function, which is integrating the velocity function. So here's a graph that we drew of everything that the helicopter is doing. So the helicopter is obviously moving upwards and flying across the distance to get to the rover. So we have x initial and x final. So this would be, our x initial would be 0, and then our x final would be 100 meters. And then we have a y initial and a y maximum for its maximum height that it reaches. And you can see that right here, the slope would be 0 at the highest point of the graph. And then our y final, which would also be 0 when the helicopter lands. And then we have our position function, so our r of t, and you can see how it would be integrated out, and you can plug in all the values such as your known beta, alpha, and distance values into here, and then you can solve for t, which you can see over here. We have the solution after this has been solved. So we have big T, which is how much time is the helicopter in the air, and we ended up getting square root 3 times the distance of 100, and then over 2 beta. So then we talk about where does it land. We need to know our delta y and delta x. So our delta y, we got alpha over 35 beta multiplied by the distance, and then for our delta x, we have that equal to the distance, which is equal to 2 beta times t squared over 3.
So in terms of the units, we know that acceleration, the units for acceleration are meters per second squared. And we know that the units for time, so that includes both little t and big T, is seconds. And during this exercise, we had to figure out what the units were for both alpha and beta. And we determined those to also be acceleration meters per second squared. And we figured this out by basically saying that in this equation, the two t's, they both have units of seconds, and so they cancel out. And in order to get meters per second squared for the acceleration, both beta and alpha also need to be meters per second squared. And also in this equation, we had both symbols for the x-axis and the y-axis. And this is how we determined that the alpha it represents the acceleration for the y-axis, and beta is the acceleration on the x-axis. So we have chosen numbers for each of the variables. So beta is 4 meters per second squared, alpha is 7 meters per second squared, and d is 100 meters. And we plug all of this into the equation for big T, which is the amount of time spent in the air. And we know that we have to get to seconds at the end, and the way that we do this is the meters cancel out, and then you square root the seconds, which gets you about 6 seconds, which for a lightweight helicopter, going 100 meters in 6 seconds seems pretty reasonable. In terms of our equation for big T, if you increase the distance, this also means that the amount of time spent in the air increases as well. And this is because the more distance you have to cover, the more time it's going to take to cover that distance. And then when the acceleration on the x-axis, which is beta, when that increases, then big T, the amount of time spent in the air, that decreases. Because the faster that you accelerate, the less amount of time it's going to take for you to cover that amount of distance. And then in terms of our equation for the change of y, when you increase the acceleration on the y-axis, this also means that you increase the change in y. And this is because when you accelerate up more, this means you're going faster, which means that you're also going to go higher. And if you increase the acceleration in the x direction, this also means that you decrease the change in y.
Okay, so for project 1, part of the solution was to find a problem that was pretty similar to the Mars rover problem that we solved. And so what we identified was the Super Mario problem that was solved in class. And some beginning similarities here is that they're both acceleration problems, and they both ask for the final position. So for Mario, to get the final position, you had to integrate twice, of course, to get the velocity, and then the integration, or the integral of velocity is the position function. And then from that, solving symbolically, you'll cancel out the little t and you'll get that as the final solution. And so the similarity here is that the same thing happens and little t gets canceled out when integrating and finding the delta x, or the change in x of the position. And so a difference here is that there was also a y, which makes sense because the Mars rover helicopter is moving up and in the x direction, where Mario is just moving in the x direction. Now, some other differences is that there are some extra known constants, alpha and beta, for basically the acceleration is kind of alpha, and beta is the acceleration for the Mars rover. Now here we have the initial acceleration, which is different from beta and alpha. And then Super Mario's problem also asks for a constant acceleration problem if Mario's acceleration was constant. So instead, you had to do some extra steps using the constant acceleration equations to find Mario's position, where all we had to do for the Mars rover was integrate twice, solve for some variables. Now, the big T is a similarity that I forgot to cover, and that is an unknown constant. And so both of these problems involved solving for big T so you could get a symbolic answer, and then finally solve for the position.